So I'm sure a couple of you are thinking right now, oh my God, what is this? This looks like magic. How does this even work? How can I be assured that if I write this, this is going to work? And that's a great question. How do you prove that a recursive method is correct? Well, in mathematics, if you haven't taken Math Concepts 2 yet, you're going to learn about something called proof by induction. Now, the way proof by induction works says that basically you have this base case. We prove that we are given this mathematical theorem, and we show that it's true for some base case. Like, we have this equation. It says, like, if we do these things to n, it's equal to this equation. Right? This one side of the equation is equal to the other side of the equation. And the base case is like saying you've got this given that if n is equal to 1, then we get this value out. Okay? And what proof by induction says is that it shows that if you assume that it's true for n, then that will prove that it's true for n plus 1. So that way, knowing that, and so once you prove that if it's true for n, it's true for n plus 1, you can say if it's true for 1, then it's true for 2. And if it's true for 2, it's true for 3. And if it's true for 3, it's true for 4, and all the way up the chain. So if you've studied proof by induction, there you go, that's a review. If you haven't done proof by induction yet, that's okay, but that was probably worthless to you until you take it. And in case you can, refer back to this, and suddenly things are going to just start falling into place. So the recursive proof is very, very similar to induction. We want to show that basically the base case is correct, right? The summation from 1 through n, right? Well, if it's less than 0, it's not going to be a summation from 1 through n, so we're just going to, right, if n is less than 0, there can't be a summation from 1 through n, so so we're just going to return 0 there. What about if n is equal to 0? Well, that's not going to add anything up, so also 0, right? That's correct. So that's where we've got our base case. So that's why we have that as our base case. Then what we want to show is that, okay, the base case is correct. Now we have to show that every recursive case makes progress towards our base case. Right? So if we start at n, then if we start at summation n, then we're going to call n plus summation n minus 1, which is going to call n minus 2, which is going to call n minus 3, which is going to call summation of n minus 4, and so on and so forth, until n minus some number is equal to our base case, right? So eventually we're going to hit our base case. Similarly with our print characters, right, we're going to start with maybe a string that's n characters long, then we're going to call it on something that's n minus 1 long, then n minus 2 long, then substring so that it's n minus 3, then n minus 4, then n minus 5, and so on and so forth until we keep removing characters until we get to the empty string. So each time, so we're essentially, we're saying is, how can we be assured that we're not going to be hitting an infinite loop here? So that's what we're doing here. The next thing we want to do, and then factorial we'll just go over here, right? We're given a positive number, a non-negative number, right? 0 factorial or 1 factorial, they're both equal to 1. If we get that, we return 1. Otherwise, we're returning n times n minus 1, which will return n minus 1 times n minus 2, which will return n minus 2 times factorial of n minus 3, and so on and so forth, right? Factorial will call factorial, which will call factorial, which will call factorial, but each time the number that gets passed in will get smaller and smaller and smaller. Okay, and now the last part is to show that it's true, or that it's going to work, is that, well, we got to make sure that if all the problems that are all solved correctly, then if we put if we break it apart like this, will it be put back together in a appropriate answer? And so for factorial, right, we're multiplying 5 times 4 factorial a lot of times in our example. And 4 is equal to 4 factorial is equal to 4 times 3 factorial. 3 is equal to 3 times 2. So we're just multiplying these products together, and that will get us our, so we know that multiplying 5 factorial is the same as multiplying 5 times 4 factorial, and which we, I just went over the recursion of that. And then we get 4, and we know that that's the same as saying 5 is equal to 5 times 4 times 3 times 2 times 1, and that's the equivalent of what's going on there. So similarly, when we're going through the length, we're just simply adding one for each character, right? So adding that sum together, it puts it up into a correct number. So that's what it means by proving that it works. That's showing that basically if we combine our answers together, then we've got an actual solution, right? So this is their diagram of tracing the recursion, right? For instance, so just to review, for instance, if we call the length function on ACE, it will return, that does 1 plus the length of CE, which does 1 plus the length of E, which it will return 1 plus the length of empty string, which is 0. So it'll return 1 plus 0, which returns 1 over here, which will return 1 plus, well, this was 1, so it will return 2. So length of ACE will return 1 plus 2, which will return, and so length of ACE returns 3. So this kind of tracing this and computing the partial results, it's sometimes called unwinding the recursion. So now we need to talk about what happened here, what happened earlier when I called foo, right? When I called foo, I got an error much earlier, right? And just to memorize, not memorize, but refresh your memory, right? If we called foo, right, we were getting this weird thing that happened where we get an error. It's not really weird, but rather than running in an infinite loop, we got these errors upon errors upon errors upon errors, right, as it was printing out. So our next video is going to discuss the stack overflow exception.